This video is about double 10 frame flashing. The double 10 frame is commonly used in mathematics education in the early grades. Often it is used as a way to emphasize the relationship between 10 and the teen numbers by always showing a teen number by filling up the first frame with 10 and then using the second frame to show the remaining part of the number. In this video, we describe an instructional activity that uses the double 10 frame in a different way and for a different purpose. The activity we describe is designed to promote children's development of thinking and grouping strategies and of number facts to 20 through number relationships rather than through memorization. In this way, children develop a mathematical world of numbers that they can use flexibly as the need arises. We devoted an earlier video to the single 10 frame. That video includes important information about the types of arrangements of chips that we recommend and why, and it describes in detail what children learn from working with the single 10 frame activities we present. If you have not already viewed the single 10 frame video, you might want to stop here and view it now. We will not repeat all of the information in that video here, but we will include details that are essential to successful use of the double 10 frame activity we're going to describe here. Significantly, our use of the single 10 frame and also the double 10 frame does not involve having children fill up frames with chips themselves, but rather involves activities in which children see and use frames that already have chips or dots filled in. In fact, children do not even have frames to use at all. This is deliberate. In this way, the teacher retains control of how the quantities in the frames are presented to the children. As you're going to see when we describe the double 10 frame flashing activity, the ways we show quantities in the frames are deliberately chosen to advance our purposes of fostering thinking and grouping strategies and number facts to 20 through number relationships. In this flashing activity, the teacher flashes a double 10 frame containing chips shown in some arrangement she has deliberately selected. The visual material is shown briefly, say 2 to 3 seconds. Then it's removed from view for a short time, maybe 5 to 6 seconds, and the process is repeated for up to 3 or 4 peaks. The purpose of flashing the image rather than simply showing it is to promote mental imagery and non-counting approaches. The class then engages in a discussion about how many chips there were and how they figured it out. Before we discuss how children solve these flashing tasks, what that reveals about their current understandings, and what they might learn, we want to explain a few details that the teacher needs to be aware of. First, if the class has not already been introduced to a 10 frame, it is important to do so. The discussion should include that each column consists of 5 boxes and that each frame contains a total of 10. Here we show a double 10 frame. The next detail is a very important one. It is how to decide which patterns to use to show the quantity within each frame. Remember that one of our purposes is to foster children's development of number facts to 20 based on number relationships. With that in mind, we show a number within a frame in one of 2 ways, either as 5 referenced or as doubles referenced. Let me explain. To show a number as 5 referenced, fill a column of 5 if possible, and then show any remaining chips in the second column. To show a number as doubles referenced, fill the columns equally, and if the number is odd, place an additional chip in the first column. Here you see an example showing a doubles referenced 7 and a 5 referenced 7. There's great value in being consistent in the ways you show the quantities within each frame. For example, to show a 5 referenced 7, you could fill up the first column of 5 with 2 in the second column, as shown here, or you could fill the second column of 5 with 2 in the first column. But there's no added learning in doing so. Our purpose of having children learn to think of 7 as 5 and 2 and use that to reason with is not in any way enhanced by varying the way the 5 and the 2 are shown. Likewise, when showing 7 as doubled referenced, be consistent. For example, if you show 4 chips in the first column and 3 in the second, do so consistently. Another important detail is about the colors of the chips you use. Again, remembering that one purpose is to promote the development of number relationships to 20, it is essential that the chips in the 2 frames show up as distinct quantities. That is the reason for using chips of one color in one frame and chips of another color in the other frame. Doing so also facilitates communication by making it possible to ask about how many there are of each color. As an aside, we remind teachers that children that are colorblind cannot distinguish between red and green, so it is important to avoid using those 2 colors together. Well, what do children do? Let's take a look at the example we showed earlier. It will be the first task in a sequence of 3 we will discuss. When called on, Travis said, "I got 9. I counted them. I started with the yellow ones, and the first time you showed it, I counted up to 4. Then the next time you showed it, I counted the rest of the yellow chips, and I got up to 6. The third time you showed it, I counted the red chips, and I got up to 9. You turned it off before I had time to finish counting them all." Most classrooms will have at least one student that use a counting all approach, like Travis did. In fact, we often see children that use that approach pointing in the air as they count the chips, continuing on each time the image is made visible again. We can see them moving their fingers and their hands as they count the chips in the air. These children have not yet developed mental imagery for the individual quantities in the 2 frames. These children would benefit greatly from the single 10-frame activities described in a separate video. However, if the class had previously used the single 10-frame activities, most children would have mental imagery for quantities to 10 based on the 10-frame and would see the first frame as showing 6 and the second as showing 4. For these children, their task is to figure out how much 6 and 4 make together. And that is the purpose of using the double 10-frame activity. Our goal is to foster children's development of ways to figure out the totality using approaches other than counting all. In this case, the teacher would acknowledge what Travis said by saying, "Travis counted. Who figured it out without counting?" Notice also that the teacher does not work with Travis until he gets the correct solution. He will figure that out as the discussion progresses. And there's no learning benefit for Travis or for the rest of the class for the teacher to pursue the discussion just with Travis. In response to the teacher's question, "Who figured it out without counting?" Jasmine replied, "I saw 6 yellow chips and 4 red chips, and I know that 6 and 4 make 10. We would expect that a number of children might have figured it out just like Jasmine. In fact, the teacher might ask for a show of hands, "Who figured it out like Jasmine?" And then say, "Did anyone have a different way of figuring it out?" Troy might say, "I thought of moving the red chips over to the frame with the yellow ones. I put them under the yellow chips and it filled up the frame, so I knew it was 10. Troy's solution is interesting because it relies on the structure of the 10 frame. Whereas Jasmine just knew that 6 and 4 make 10, Troy made use of the fact when the frame is full, there are 10 chips. As we consider other tasks and other solutions, we will see that this type of solution can promote children's development of splits of 10 as well as of grouping strategy solutions. For this reason, the class will benefit if the teacher calls attention to Troy's solution to ensure that everyone understood his reasoning. She can even move the red chips to the first frame to show how it is filled up by the 4. It is important to devote sufficient time to the discussion so that children understand how others thought about the task, because it is through listening to and trying to make sense of what others say that children advance in their own reasoning. The purpose of the discussion is not to see if the children get the correct answer. It is to promote learning. Teachers typically use more than one double 10-frame flashing task in a lesson. Here we show a task the teacher might use immediately following the example task. In the process of explaining the solutions children might give, we clarify the importance of using a carefully thought out task sequence. The teacher poses this task by flashing it 3 or 4 times and then calling on children's solutions. Remember that a solution means telling how many chips there are and explaining how you figured it out. Our goal is to foster non-counting solutions, and for this reason, it is very important that the teacher calls for solutions while the image is left off. If the teacher begins the discussion by first turning the image back on again, children can simply count what they now see, and we will have no idea of the type of mental imagery they developed, if any, or of how they figured it out without counting. As the discussion progresses, it is important that the image is made visible again so that children can make sense of what they hear others say. What do children do? Here are some solutions we would expect. Lourdes: I saw 11. I saw that you had one more chip than last time, and that was 10. 10 and one more is 11. Nicholas: I took 4 of the red chips and moved them over to the side with the yellow chips. That made 10. And then I had 1 red chip left over, so it's 11. Sam: I put 5 of the yellow chips with the 5 red chips to get 10. I have 1 more yellow chip left, so there's 11. Maya: I know that 6 and 6 make 12, so 6 and 5 has to be 1 less. It has to be 11. Jose: I know that 5 and 5 make 10, but this is 6 and 5, so it has to be 1 more. It's 11. Now, if we take a look at these solutions, we see that those given by Lourdes, Nicholas, and Sam used the chips to figure out the total, but none of them mentioned the individual quantities involved in the frames. Maya and Jose, on the other hand, didn't make mention of the visual imagery of the chips, but they talked about the quantities represented by the visual imagery. They each explicitly talked about 6 and 5, making 11. These might seem like small differences, but they are significant and help to clarify how it is that this instructional activity functions to advance learning. Here's what I mean. One purpose of the double 10-frame flashing is to promote children's development of number facts to 20 based on number relationships. For this reason, it is important that through the discussion, the solutions Lourdes, Nicholas, and Sam gave are related to the number fact 6 plus 5 equals 11. That will happen as their solutions are clarified and elaborated, either by the teacher or other children. For example, the teacher or some other child might say, Lourdes said that last time we had 6 and 4. This time we have 5 instead of 4. We have 6 and 5, so this time it's 1 more, it's 11. Notice that this is not at all what Lourdes said. Lourdes never said that she saw 6 and 5. All she said is that she saw 1 more chip. But this recasting of Lourdes' solution is significant and powerful. It makes explicit for Lourdes and others exactly where the 1 more was. There was 1 more on the frame that previously had 4, so now it has 5. To further clarify, the teacher can remove the extra chip to show 6 and 4 and then put it back to show 6 and 5. Through this elaboration of Lourdes' solution, what was originally only about chips has become about numerical quantities. Before we leave our discussion of Lourdes' solution, I want to make one additional important point. We said that one purpose of the double 10-frame flashing activity is to promote the development of thinking strategies. Let me explain what we mean by thinking strategy. It's a technical term. It doesn't just mean that a child was thinking. We say a child uses a thinking strategy if he or she solves a task by using something they already know or have just figured out. One example of a thinking strategy is one we call the +1 thinking strategy. Here's an example of the +1 thinking strategy. If a child just knows that 6 + 6 = 12, or if he has just figured it out, he might solve the task 6 + 7 by reasoning that it's just one more than 12, so it's 13. He didn't figure out 6 + 7 as a standalone task, but did so by relating it to something else, in this case 6 + 6. You can see that by posing the double 10-frame flashing task with 6 yellow chips and 5 red chips immediately following the task with 6 yellow chips and 4 red chips, we've created exactly the type of situation where the task at hand can be related to the immediately prior task. We've created a situation where the visual image highlights the change to one more. Now, typically, we say that a child has used a thinking strategy when the tasks are posed in purely numerical form. So we would not argue that Lourdes reasoned using the +1 thinking strategy. However, we can say that this type of task sequence can be the genesis of children's development of the +1 thinking strategy. In the flashing task, it is more likely that it is the visual imagery that prompted Lourdes to know that the answer was one more. However, the teacher's recasting of Lourdes' answer brings the numerical aspect to the forefront. In fact, the teacher might write the number sentences 6 + 4 = 10, so 6 + 5 = 11, while saying, well, we already figured out from the last task that 6 + 4 = 10. This time we have one more. We have 5 instead of 4, so Lourdes figured out that 6 + 5 has to be 11. But we caution teachers not to use numerical notation too early. We will say more about numerical notation later in this video. Further, we want to emphasize that in the double 10-frame flashing activity, children never have paper and pencil, so they will never write anything down themselves. Now let's take a look at some of the other solutions to this task. Nicholas and Sam also gave solutions based on the visual imagery of the chips. Just as for Lourdes' solution, it is important that through the discussion, Nicholas' solution and Sam's solution are linked to the number fact 6 + 5 = 11. These two solutions are based on a different type of thinking than Lourdes, who saw one more chip. Each of these was based on filling up a frame to get 10. Let's take a closer look at Nicholas's solution. Notice how it is similar to the solution Troy gave for the task that showed 6 chips in the first frame and 4 in the second frame. Troy thought about moving the 4 red chips from the second frame to the frame with 6 yellow chips to fill it up. We said that solutions of this type foster children's development of splits of 10 and of grouping strategies. We say a child used a grouping strategy if he or she partitions or splits one or more of the numbers involved into parts and then recombines them in some way. In this case, the number 5 is partitioned or split into 4 and 1. The 4 is combined with the 6 to get 10, and then the 1 is added to the 10 to get 11. Nicholas didn't use the language of splitting the number 5, but talked instead of moving part of it. Now, just as with Lourdes' solution that we have just discussed, we would not say that Nicholas reasoned using a grouping strategy. His solution could have been based entirely on the visual imagery of the 10 frames. But it is the structure of the 10 frames that made it possible. Nicholas's way of thinking can be the genesis of children's development of a grouping strategy. In this case, a grouping strategy that we call filling up the 10s. For example, the teacher might say, Nicholas thought of taking 4 from the 5 and putting it with a 6 to make 10. He added on the 1 that was left from the 5 with a 10 to get 11. And the teacher can use the notation shown here as she speaks, although teachers often wait to use this type of notation until they have already used the double 10 frame flashing for several days. We will say more about this later. Likewise, it is important that Sam's solution, I put 5 of the yellow chips with the 5 red chips to get 10. I have 1 more yellow chip left, so there's 11, is linked to in the discussion to numerical quantities so that it becomes more than about seeing chips. As with Nicholas's solution, it is useful to ensure that the teacher actually moved the chips to show that they filled up the 10 and to show that 1 yellow chip remained. And it is important that Sam's solution is recast as taking 5 out of the 6 and putting it with the other 5 to get 10, with 1 left over, giving 11 in all. In each of the last 3 solutions, I've said something about the importance of recasting what was initially only about chips so that it is linked to numerical quantities. One way for that to happen is for the teacher to reframe what the child said. However, another way that is often much more effective is for the teacher to ask the class what they understand about how the child figured it out. For example, what do you understand about how Sam figured this out? If no one replies, the teacher can then call on some child specifically to reply. After using this approach several times, students realize that they are responsible to try to make sense of what others say. Further, as they then go on to explain what they understood, they do so in their own words. They say things in a different way, or they may ask questions of the child that gave the solution in the first place. As the discussion progresses, the teacher can take note of what is said, and if necessary, add her own remarks to ensure that the relevant numerical quantities are referenced. Before we leave our discussion of this task, let's go back to look at the solutions given by Maya and Jose. Both of these children figured out the task by relating it to something they already know. While the visual imagery may have played some role in their thinking, the solutions Maya and Jose gave show that both of them already have some well-developed number relationships that they can use without prompting. We know that these ways of thinking become increasingly common as the teacher continues to make use of this flashing activity. Let's consider a third task the teacher might use in the same lesson. We've talked about how following the double 10 frame that showed 6 and 4 with one that shows 6 and 5 has the potential to lead to thinking that can serve as the genesis for the +1 thinking strategy. Now suppose we follow the task with 6 and 5 with 7 and 4 as shown here. How might children figure this one out? Based on our experience in classrooms, we would expect the following solutions. Maria might say, I know that 6 and 4 make 10, so 7 and 4 has to be 1 more. It has to be 11. Xavier might say, this is like the first one we did. If you take off 1 yellow chip, it's the same as the first time. That one was 10, so this one has to be 11. Amber might say, I thought of moving 3 of the red chips into the first frame with the yellow ones to fill it up. That makes 10. Then there's 1 more red chip, so it's 11. Destiny might say, I put 6 of the yellow chips with the 4 red ones to get 10. I have one more yellow chip left, so there's 11. Katie might say, well, it's just like the last one. If you move one of the yellow chips over with the red ones, it will be 6 and 5, just like last time, so it's 11. The solutions given by Maria, Xavier, Amber, and Destiny are similar to those we have already discussed for tasks 1 and 2. But Katie's solution is of a different type. Katie thought of moving a chip from one frame to another, but not for the purpose of filling up a frame to get 10 like Amber and Destiny did. Rather, she thought of moving one chip from one frame to another to make it look like the previous task. Katie's solution is based on relating this task to the prior task, and as such, it falls within what we think of as a thinking strategy type solution. I say a thinking strategy type solution because Katie's reasoning is based on the visual material of the chips, not of reasoning entirely numerically. Let me explain what I mean. Suppose the teacher poses the task 6 plus 6 purely numerically, and the class agrees that the answer is 12. And then the teacher poses the task 7 plus 5. If a child says, well, this is just like the last one because you can take 1 from the 7 and put it with a 5, so now we have 6 plus 6, just like last time, so it's 12. We would say the child used a thinking strategy. In this case, we call it the compensation thinking strategy. The child adjusted the first number in the task, 7, by decreasing it by 1, and compensated for that by increasing the second number in the task, 5, by 1. Now the task has been changed from 7 plus 5 to 6 plus 6, something that has already been figured out. How do children develop thinking strategy ways of reasoning? The argument I am making throughout this video is that when children solve double 10-frame flashing tasks by relating them to a prior task, it is the visual imagery that drives their thinking. But that type of thinking is the basis from which thinking strategy reasoning develops. And as I said when discussing Lourdes' solution earlier, the teacher can play an important role by recasting or restating the children's solutions in numerical terms. For example, here the teacher might say, Katie thought of it like this. She thought, I can move one of the yellow chips over with the red ones. Then I will have 6 in the first frame and 5 in the second frame. That's what we had last time, so this has to be 11. What is happening here is that the teacher is relating Katie's solution, which was based on visual imagery, to the quantities represented by the visual imagery. And in this way, she is making explicit the numerical relationships between this task and the prior task. The teacher will surely move the chips to clarify how Katie reasoned. The teacher might also choose to use notation as she recasts Katie's solution in numerical terms. We caution teachers not to use numerical notation too quickly. Children need to focus their attention on the visual material and begin to think in terms of quantities as well as in terms of chips before the teacher brings in numerical notation. Let's take a minute to review the entire sequence of tasks we have just discussed so far. Here you see the 3 double 10-frame tasks in the order they were used in the lesson. As our discussion has shown, we have deliberately chosen these 3 tasks in this order to create opportunities for children to solve the tasks by relating them to one another. And we have argued that doing so forms the basis for children's eventual development of thinking strategy reasoning. Further, the structure of the 10 frames creates opportunities for children to solve the tasks by moving chips from one frame to another to fill up the 10. In this way, the tasks provide the basis for children's eventual development of the filling up the 10 grouping strategy. These ways of reasoning are very powerful, and once children have developed them, they can easily and quickly figure out various sums. In particular, this type of reasoning can be the basis for children's development of the number facts to 20. We know this from extensive experience in the classroom, that children become so adept at reasoning in these ways that over a short amount of time they come to just know the basic number facts to 20. And if asked, they are able to explain how one might figure out those sums. In other words, the child has a well-developed set of number relationships that he or she can use in flexible ways. Another way to say it is that this approach to developing number facts to 20 provides children with a basis for a broad and flexible range of mathematical reasoning. And in this sense, taking the time to develop these ways of reasoning is time well spent. The child is building up a mathematical world that he can navigate in a variety of ways. As such, the child knows far more than if he simply memorized number facts. For this reason, we urge teachers to plan sequences of this type. Throughout our discussion of children's solutions, we have referred to possible notation the teacher might use, but we've given the caveat to not use notation too early. In our view, many instructional materials introduce children to notation far too early. For example, often tasks are posed entirely numerically well before the child has a well-developed concept for the quantities involved. For example, if a child sees the number sentence 6 plus 5, what might this mean to the child? Certainly, we want much more than that the child can correctly say or write 11 is the answer. It is important that the child's numerical world is based on much more than memorization. The approach we advocate is that numerical notation and number sentences are linked to reasoning children engage in, and as such are records of their reasoning. In other words, the reasoning comes first, and the written record only after that. At the same time, the child has to be introduced in some way to written numerical notation. In the examples we have discussed, we have shown ways the teacher can use written notation to show reasoning that a child engaged in or that emerged through the class discussion. In some cases, the notation is not entirely conventional, as for example when we include arrows to show moving part of one quantity over to the other. But such notation is meaningful because the child talked about moving one amount over to the other. And we remind teachers of what we said earlier. Children never use any notation themselves during this activity because they are reasoning entirely mentally. They do not have paper or pencil to use. We suggest that teachers use their judgment about how soon to introduce written notation of the type we've described. It is important that the children focus on the reasoning first, and once they are familiar with talking about their ways of reasoning and about quantities, not only about chips, it is appropriate to use notation. Second grade teachers often find it appropriate to begin using notation after just a few lessons. First grade teachers often do not use any notation at all. There's another important reason for introducing written numerical notation. As children become familiar with it and how it can be a record of their thinking, the notation itself comes to have meaning for them. And it is at this time that it is appropriate to pose tasks in purely numerical form. So after using the flashing task for a while, along with written numerical notation, we suggest posing tasks without using the 10 frames. In the whole class setting, pose a task such as 5 plus 5. Most children will just know the answer, so there will be not much to say. Follow that task by 5 plus 6. Now some children will just know this as well, but some will point out that it's just one more than the last one. In other words, they are reasoning using a thinking strategy approach. Another approach that is very useful, and one that we actually prefer, is to pose tasks that involve 3 numbers, such as 6 plus 5 plus 4. or 9 plus 6 plus 5. Again, children are expected to solve these tasks entirely mentally. They have no paper or pencil or any other materials to use. We can learn a lot from listening to how children figure out these tasks, and children can learn a lot from solving them and from listening to how others solve them. I have included this brief discussion of the activity we call number sentence without counting. We call it that because children are told to figure it out without counting. Because the ways of reasoning that children develop from engaging in the double 10 frame flashing task are precisely the ways of reasoning that they can then use to solve these number sentence tasks. Wouldn't you be thrilled as a teacher if later in the school year a child solved the task 99 plus 47 by saying, I know that 100 plus 47 is 147. So 99 plus 47 has to be just one less. It has to be 146. Or if someone said, I moved 1 from the 47 over to the 99 to make it 100. Now I have 100 plus 46, so it's 146. I want to include an important caveat here to be sure that we are not misunderstood. We are not suggesting that you teach the +1 and the compensation thinking strategies or the filling up the 10 grouping strategy, and we are certainly not advocating that you use that language, although it's possible that somebody might say things like, Maya just knew this was 1 more than last time, or David filled up the 10s. What I am saying is this: we know from extensive experience in many classrooms that these ways of reasoning will emerge from using the double 10 frame flashing activity. When will you use the flashing activity? In our experience, many second grade teachers use it several times a week for the first 2 or 3 months of the school year, devoting about 15 minutes of their lesson time to it. In fact, one second grade teacher we worked with used it successfully 45 times, starting at the beginning of the school year. As we've just commented, it can gradually give way to the number sentence without counting activity, but even so, it is helpful to continue the flashing activity as long as our least sophisticated students are learning from it. As with any instructional activity, it is time to discontinue it when children are no longer learning anything new. First grade teachers often use double 10 frame flashing sometime later in the school year. Many teachers have told us that this activity is one of their favorites. It is easy to plan and to conduct, and it is very apparent that children learn much from engaging in it. Finally, we encourage teachers to consider using the 10-frame games that are described in the single 10-frame video in lessons when they use the double 10-frame flashing activity.